Hello students, welcome to my channel. Today I am to discuss a topic from B.Sc second year physical chemistry, that is the partially miscible liquids. First of all, I would like to tell you about the term miscibility. Miscibility से हमारा क्या मतलब है? Miscibility is a phenomena in which two or more liquid get mixed up and they form a solution, a homogeneous solution. Okay, so the miscible liquids are of three types. One is the completely miscible, and another category is the immiscible liquids. Okay, so what are the immiscible and the immiscible liquids? Immiscible liquids are those in which the two or more liquids they get completely mixed and form an homogeneous solution. Okay, on the whereas other side, the immiscible liquid are the two liquids which do not mix at all and form two distinct layers. Okay, now the third category is the between these two liquids, that is completely miscible, and the immiscible liquid, that is known as the partially miscible liquids. It means these are those liquids or the two or more liquids which shows a limited solubility in each other. Okay, for example, the mixture of phenol and water. Let me discuss this mixture in detail. So if we have a phenol water system which is a partially miscible liquids, so in a phenol water system, initially if we add a small quantity of phenol in a beaker of water, then initially what will happen, the small quantity of phenol, it will dissolve in this water mixture, a water solution. Okay, however, on the further addition of phenol, a stage is reached when no further dissolution takes place and the two solutions they will form the two separate layers. Okay, so in the above layer it will be a water, it will be a phenol in the lower layer, and this lower layer will be saturated with water and the upper layer will be saturated with phenol. Okay, and a stage is reached when both layers will be in the equilibrium. At that stage is known as the conjugate stage or the solution in that case will be known as the conjugate solution. Okay, at that stage the composition of both layer will depends upon the two factors, that is temperature and pressure. What does it mean? It means at a constant temperature the composition of each layer remains constant as long as the two phases are in equilibrium. However, as the temperature is increased, suppose we are increasing the temperature of this system, what will happen? There will be the mutual solubility of the two layers, it will goes on increases till at a particular temperature the two layers becomes completely miscible and the solution has an identical composition throughout. Means if we increase the temperature of this system, what will happen? Both the layers will be getting miscible with each other and a homogeneous solution will be formed. That means you cannot see a distinct boundary at that temperature and the solution will be a completely clear solution. In that case the composition of water and the phenol will be equal in the above and the lower layer. Okay, that temperature is known as the critical solution temperature. Means the critical solution temperature is that temperature at which both the solutions they forms a clear miscible solution. Okay, and depending upon the nature of the liquids, the two liquids layer which becomes completely miscible with each other depends upon, means the critical solution temperature is the temperature at which the partially miscible liquids become completely miscible in all proportions is called as the critical solution temperature. Okay, and depending upon the nature of the liquids, the two liquid layers may become completely miscible either at a temperature lower than that the ordinary temperature or at a temperature higher than the ordinary temperature. Means either by cooling the solution. Okay, there are so many examples in which the two layers which are initially having the partially miscibility with each other, if you lower the temperature of that system, they becomes miscible. And there are solutions which are miscible at higher temperature. Okay, there are few solutions there which are initially partially miscible, but they show the miscibility at a lower temperature as well as upper temperature. Okay, that means at the both lower and the upper temperature they show the miscibility. Okay, on the basis of these natures we have divided these critical solution temperature into three categories. First category is the systems having an upper critical solution temperature. Okay, second category is the system having a lower critical solution temperature, and third category is the systems or the system which is having both upper and lower critical solution temperature. Let us discuss in detail these three types of systems one by one, and in this video I am going to discuss only the first part, that is the upper critical solution temperature, with a suitable example. Let us take the example of phenol-water system. This system is a typical example of upper critical solution temperature. Here the phenol and water are partially miscible at ordinary temperature, as I already have told you, and when equal volumes of phenol and water are mixed, that means if we take the 50 ml of phenol and 50 ml of water, okay, the two layers are formed, and the upper layer is saturated solution of phenol in water, and the lower layer is a saturated solution of water in phenol. Means small amount of phenol will go into the water solution and the small amount of water will go into the phenol solution, and both will be a saturated solutions and there will be a distinct boundary between them. Okay, and these solutions are in equilibrium at this point when they form the saturated solutions. Okay, that means they are known as a conjugated system or conjugate solutions. Okay, now at a given temperature, let us say the temperature of the system is 20 degrees Celsius. At a given temperature, the composition of the two layer will be fixed. The addition of either the small amount of water or small amount of phenol, okay, if you add the small amount of water and small amount of phenol, it does not change the composition of phenol in water and the phenol in water in phenol. Means it just merely increase the volume. If you add the phenol, then it will increase the volume of phenol, or if you add the water, then it will increase the volume of water in the water layer. It does not affect the concentration of phenol in water or water in phenol. Okay, however, on increasing the temperature of the system, the mutual solubility of phenol and water will increases. Okay, and at a certain temperature, the composition of the two conjugate solutions becomes same, as I already told you, and that temperature will be known as the critical solution temperature. Let me explain this phenomena with the help of a diagram. Here I am writing the percentage by weight of phenol which is going to increase on this side. Okay, let it is a 0, it is a 20 here, 40, 60, 80 and 100. Okay, and in this side I am writing the temperature. This 20, 40, 60, 80 and 100. Okay, let us suppose here we have the temperature is 20 degrees Celsius, and at that point there will be a very small amount of phenol in water, and on the other side if I plot the phenol in water, then it will be having, let's start from here, and it is here we have a water in phenol. Okay, and here it is phenol in water. With the increase of temperature, what will happen? The phenol in water concentration will increases, and from this side the water in phenol will also increase. Okay, and at a temperature around 66 degrees Celsius, what will happen? The two layers just get miscibility, maximum miscibility. Okay, if you increase the temperature further above the 66 degrees Celsius, there will be only a one layer, and there will be a parabola type graph which represent that outside this graph there will be a one layer which is a homogeneous layer. Okay, and inside this parabola there will be two layers, two saturated layers. That means in this area there will be a heterogeneous solution. Okay, and on the outside of the on the left side of this graph, that is at point A, there will be a more water and less will be the phenol. Okay, and outside this on the right side there will be a more amount of phenol and less amount of water. As the temperature increases, the miscibility of water in the phenol and phenol in water increases, and at 66 degrees Celsius, which is known as the critical solution temperature, okay, the both the layers are in equilibrium. Okay, if you increase the temperature further above the 66 degrees Celsius, then both the layer will be completely miscible with each other and only form a one layer solution there. Okay, and at that temperature the composition of phenol in water will be around 34%. Okay, so what features of this solubility curve shows, I am writing here one by one. The point B here, and we have a point C here. Just I am drawing a line from 40 degrees Celsius, and the point here where the two lines intersect, that is known as the point C. Okay, let me explain all these points. The point B in this graph represents the upper critical solution temperature, which is around 66 degrees Celsius and having a composition of 34% by weight of phenol, and this composition is known as the critical composition. Okay, second point, above 66 degrees Celsius, the phenol and water are completely miscible and form a single solution. Okay, now the point third, which is the outside the curve, as I already told, the system will be homogeneous system. Okay, and consist of only single liquid phase. Earlier it was having the two liquid phase, one here the phenol in water and here it was water in phenol. Okay, outside the curve, that is above the temperature 66 degrees Celsius, there will be a homogeneous system and it will having only single liquid phase. Okay, number 4, Any point within the curve represents the two layers in equilibrium with each other, that is inside the parabola. Just write down, any point within the curve represents two layers in equilibrium with each other. Okay, or you can say simply, inside the curve, inside the parabola curve, the system is heterogeneous. Now the point, the line which is going to intersect, that is at point X here, and we have a point Y here. Okay, now the point X represents the composition of phenol in water, and the point Y represents the composition of water in phenol. Okay, for any temperature below 66 degrees Celsius, the point A, which is here, okay, the point A on left side, what does it represent? It represents an unsaturated solution of phenol in water, and the point B on right side, it represents an unsaturated solution of water in phenol. Number 7, the point C, which was here the intersecting line, at the center of the intersecting lines, okay, at that point we can easily calculate the relative mass of phenol and water at point C on XY line, which is known as the tie line. The relative mass of phenol and water can be given by, or can be calculated by, a rule that is known as the lever rule, and according to this rule, the mass of phenol layer upon the mass of water layer will be equal to Cx upon Cy. Okay, and this is all about the phenol water system. These are few more examples of solutions having the upper critical solution temperature, just like the aniline water system, in which the upper critical solution temperature is around 168 degrees Celsius, and at that temperature the critical composition of first component, that is aniline, is around 40%. Similarly, we have a aniline hexane system, and its critical solution temperature is 59.69 degrees Celsius, which is having the 52% of aniline at that temperature. Similarly, methanol and carbon disulfide system, methanol and hexane, which are having the critical solution temperature around 40.5 degrees Celsius and 49.1 degrees Celsius respectively, and having the composition of methanol around 20% in each solution. In the next video, I will discuss the remaining two systems, that is the system with lower critical solution temperature and the system with having the both lower and upper critical solution temperatures. And if you like this video, please and share with your friends, and please subscribe my channel for latest information. Thank you so much.